4-day morning session. Just before I introduce the speaker, I want to mention a word of compliments for our young organizer for this very fine conference they have put together. It's been going very well so far, and I'm sure it will continue to go well. With that, it's my pleasure and honor to introduce the first invited speaker, Professor Gurmeet Bakshi from Panjab University, Chandigarh, who is a well-known prolific researcher who works in many areas of mathematics, and she will talk to us today about explicit computation of Wedderburn decomposition. Gurmeet.
Yeah, thank you, Professor Ghorpade, for the introduction. And I also must congratulate the organizers for organizing such a wonderful conference, and I'm thankful to the organizers for the invitation. So today I will speak on, am I audible? Hello, am I audible?
Yes.
Yes.
So I will speak on the explicit computation of Wedderburn decomposition. So what is Wedderburn decomposition? So it comes from a classical result in non-commutative rings due to Wedderburn-Artin. It's a landmark result. And some people also call it the first most important result in the theory of non-commutative rings. What is this result? It gives you the structure of semi-simple finite dimensional algebra over a field. So it tells you that for such an algebra, the structure is very neat. It's a direct sum of matrix rings over division rings. So, and these are simple rings. This is easy to prove. I mean, this comes in the first course in non-commutative rings, that these are simple rings. And there is an isomorphism. If A is a finite dimensional semi-simple algebra over F, then it is isomorphic to such matrix rings over division rings, where these DIs are finite dimensional division algebras over F. And this isomorphism, this precise isomorphism, is called the Wedderburn decomposition of A. And these matrices over DIs, they are called simple components of A. These are simple rings, they are called simple components of A. So this is Wedderburn decomposition, and these are simple components of A. And this theorem was proved by Wedderburn in 1907. And then later Artin extended this result to give description of associative Artinian rings without nilpotent ideals. So together with this generalization, it is called Vidhvanaten theorem, but initially it was given by Wedderburn. So that is why it's called Wedderburn decomposition. Now, this is the most important result in non-commutative rings. The entire study of representation theory of G over F depends on this theorem, comes from this theorem. So I will discuss the impact of this theorem in the study of group algebras. So what's a group algebra? Take any group G. Here I've taken a finite group, but group algebras you can define for any group. So take any group and take a field. Now look at finite F linear combinations of elements of G. If your G is finite, you just take F linear combinations of elements of G, and then component wise you can add them, you can multiply them using the multiplication in the group and the associativity, and that makes it an algebra over F, and this is called the group algebra of G over F. Well, it's an algebra over F. So whether this Wedderburn theorem is applicable. So when is this group algebra semi-simple? So that is the first question, and this was answered by Meshike, that the group algebra FG, I'm taking a finite group throughout this lecture, the group algebra FG is semi-simple if and only if the characteristic of F does not divide the order of the group. So under this circumstance, the Wedderburn theorem is applicable to the group algebra, and you have the decomposition of Fg as a direct sum of matrix rings over division rings. Now, this field F has lot to play in this decomposition. This is the Wedderburn theorem, and so suppose F is algebraically closed field. So if the field is big, the problem is less. if F is algebraically closed field, then you remember those DIs are finite dimensional division algebras over F, and F is algebraically closed. So DIs can be nothing except F itself. So FG is isomorphic to matrix rings over the field F, and this is the most crucial result in representation theory of groups over algebraically closed field. For example, it tells you that the order of the G is the sums of the squares of the degrees of irreducible representations, and several results in representation theory follow from this result. This is the case when F is algebraically closed, for example, complex numbers. Moving to down, suppose F is not algebraically closed. For example, suppose take the case when F is reals. Now, if F is reals, the DIs are finite dimensional real division algebras. And then there is a theorem of Frobenius which gives you classification of finite dimensional real division algebras. And these are precisely reals, complex numbers, and real quaternions. And this further divides the study into real representations into 3 different classes depending upon the kind of division algebras which you are getting. Moving still down from reals to Q, moving to F is equal to Q, the difficulty is manifold because you have to classify finite dimensional division algebras over Q. They will come into the picture. And so this is what I will be discussing in this talk. And if the time permits, I will also discuss the case when F is a finite field and the semi-simple case when the characteristic of the finite field is co-prime to the order of the group. So these are the 2 things which I want to discuss. So I have a group algebra FG, semi-simple case taking throughout. And this is Wedderburn decomposition. AIs I have just renamed as MNI, simple components. And this is the Wedderburn decomposition. Now, in the Wedderburn decomposition, our interest is also to understand that precise isomorphism. Not only that we want to understand this decomposition, what are NIs, what are DIs in terms of the group G. And we also know how this, given a group, how this isomorphisms come into the picture. And for that, we need a set of invariants of the algebra called primitive central idempotents. I will just come to that. Now, this is a semi-simple ring. So, and these happen to be minimal two-sided ideals of FG. And it's a property of semi-simple rings that every two-sided ideal is generated by a central idempotent. So with that, because this is a two-sided ideal, it is generated by a central idempotent of FG. Now, so you look at idempotent corresponding to each simple component. So if there are n simple components, I have n central idempotents which generate those simple components as two-sided ideals. And now what is the property of these central idempotents is that one is the sum of those idempotents. If you just write the decomposition of 1 and you write E1 plus E2 plus En, then you can prove that EI is precisely which generates this MNDI as a two-sided ideal. And the product is 0 because EI, EJ, this belongs to AI and it also belongs to AJ, and AI intersection with AJ is 0. This is a direct sum. So the product of EI, EJ is 0. And because of the fact that it is a minimal two-sided ideal, it turns out that you cannot break EI as sum of 2 more central idempotents. And so this set of central idempotents having these 3 properties, this set is unique and it's called set of primitive central idempotents of the group algebra FG. Once you have the set of PCIs, primitive central idempotent, then you can also write down what is this map, because it tells you how will one decompose. One will decompose as sum of EIs. So alpha will decompose as sigma alpha EI. So you will know precisely what is this isomorphism. But knowing the primitive central idempotents EI, does it mean that if you know this EI, does it mean that you know AI as a matrix algebra over DI? The answer is not always. It depends upon how you are getting the things right and what method are you applying. So if you know EI, it does not always mean that you know this as a matrix algebra over DIs. Calculating DIs, calculating the size of the matrices, calculating EIs, these are problems in itself. And I will come to the techniques which have been used for the classic. I will start from the classical method and come to the newer techniques which people are using to give this decomposition. And so these are the two cases which I want to discuss, field of rationals and the field finite field whose this order Q is co-prime to the order of the group. And this is a central problem in group rings. It is connected with isomorphism problem in group rings. It is connected with the structure of the unit group algebra. It is connected with coding theory, or when you study group algebra over a finite field, it is connected with coding theory. It is connected with the Zessanos conjecture. So this is a central problem in group rings to understand this decomposition of this algebra. So I will start with the very simple case. When you take a cyclic group of order n, what happens? Now, my aim is G is a cyclic group of order n. I want to show you how Fg decomposes as simple components as sum of simple rings. Now, x to the n minus 1, suppose you can factorize this. This is the factorization of x to the n minus 1 into irreducible factors over f. Then this isomorphism is easy to see, that this Fg is isomorphic to, this is the polynomial ring over f and quotient with the ideal generated with x to the n minus 1. And then using Chinese remainder theorem, one can prove that this ring is isomorphic to the direct sums of these rings. Now, because of the fact that this is irreducible polynomial over f, so this quotient becomes, this is a maximal ideal of this, therefore this quotient becomes a field. And so this is a field obtained by adjoining a root. Eta 1 is a root of f1, eta 2 is a root of f2, and eta n is a root of f1. And these are fields now. Fields are simple rings. So this gives you decomposition of Fg as direct sums of fields and also simple rings, because this G is commutative. So you will have the size of the matrices as 1. So this is the case when G is a cyclic group of order n. So for example, take C7, cyclic group of order 7 over Q. So this is the decomposition of x to the 7 minus 1 into irreducible factors over Q. This is x minus 1 and this is irreducible. And therefore, this will give you the decomposition QZ as 2Q, I have to adjoin a root of this, which is 1. And then 2Q, I have to adjoin a root of this, which is zeta 7. So this is the decomposition. Now, so in general, if you write QG, where G is a cyclic group of order n, this decomposition, you have to factor x to the n minus 1 into irreducible factors over Q. And then it's a well-known result. This is done in the classroom during masters when you do field theory, that this is the decomposition of x to the n minus 1 into irreducible factors. These are cyclotomic polynomials. So this is x to the n minus 1. Zeta is a primitive nth root of unity. These are all the roots of this. And now you collect those nth roots of unity whose order is d, where d is a divisor of n. Then this is what the cyclotomic polynomial phi d is, and then it's classroom result that this polynomial has integral coefficients, and this is irreducible over Q, and this is the decomposition. And once you have the decomposition, you have QG as direct sum of sum d dividing n to Q, I have to adjoin a root of phi d, and which is zeta d. Zeta d is a primitive dth root of unity. So this is the decomposition. So let's also see, for example, over finite fields, say C7 over Q, you saw Q sum Q zeta 7. Let's see C7 over F2, finite field with two elements. This is a decomposition as irreducible factors over Z, but then this polynomial is not irreducible over F2. This is irreducible over Q, but this is not irreducible over F2. This will further break into two more irreducible factors, and therefore this is now the decomposition into irreducible factors, and therefore F2G decomposes as corresponding to this component, it is F2, and zeta 7 is a root of this polynomial. Zeta 7 lies in a third degree extension of F2. So this is F2 zeta 7, and corresponding to this also you are getting F2 zeta 7. So in the QG, where G was C7, you had one copy of Q zeta 7, but now here you are having two copies of F2 zeta 7. So this was an example. So generalizing this, take cyclic group of order n over FQ. So basically this is the factorization into irreducible factors over Q, but now these are not irreducible, not necessarily irreducible over Q, and so they will further break, and so there is a Galois action, and so look at the Galois group of FQ zeta d over FQ. This acts on the roots of this polynomial by this action. And now you look at the orbits. So the roots of this polynomial get divided into different orbits, and those orbits I am just denoting by CQD. CQD is the orbits which you get by the action of this group on the roots of this polynomial, and therefore this phi dx, this I can write as this because these are all the orbits, and zeta I belonging to this orbit, and then this one can show that this is an irreducible polynomial over FQ. So this phi d will further break into irreducible polynomials. How many irreducible polynomials? As many as the orbits, and therefore you will get this decomposition. FQG is isomorphic to some d dividing n, and then FQ zeta d, how many copies? As many as the orbits. So this is the decomposition. So this is the case of cyclic groups. Moving on from cyclic groups to abelian groups. This is what Perlis and Walker proved in 1950, that if you have an abelian group, then this is its Wedderburn decomposition as direct sums of fields. Sum d dividing n q zeta d, and how many copies of q zeta d? As many as the number of cyclic subgroups of G of order d. And this matches with what you have seen for the cyclic case. For the cyclic case, you saw QCN is sum d dividing n q zeta d. So because for every divisor of n, there is precisely one subgroup of order d. But in general, you will have AD subgroups, or AD is the number of cyclic subgroups of order d. And so AD copies of q zeta d will occur in this decomposition. So let's apply this. Say, take for example this abelian group C2 cross C4 over Q. So for each divisor of the order of the group, I have to count the number of cyclic subgroups of that particular order. So cyclic subgroups of order 1 is 1. And how many subgroups of order 2 do you have? 3. And how many subgroups of order 3 do you have? 2. So in the Wedderburn decomposition, I will get one copy of Q, 3 copies of Q zeta 2, and 2 copies of Q zeta 4. So this gives you this decomposition. But as I told you, my aim is also not only in this decomposition, my aim is also to know how do I get this decomposition? What is the map which gives you this decomposition? So to understand that map, we also need to understand the primitive central idempotents of the group algebra, which will give you that map. So coming to the primitive central idempotents, first I will talk of the abelian case and then I will move on to more general groups. This is classical result in you do in the first course in representation theory, that if you have the set of all irreducible complex characters of G, see when you decompose CG you write as the direct sum of matrix rings over C itself, and the number of irreducible complex characters is same as the number of simple components of CG. And IRG I am taking as the set of complex irreducible characters of G. And one can show that if chi is a complex irreducible character of G, then this fellow 1 upon order of G, chi of G inverse G, this is an element of CG. This chi is a complex character, it's an element of CG. It's a group ring element in CG. And then it's a textbook result which you can search in all the first course in representation theory books, that it's a primitive central idempotent of the complex group algebra. But remember, my aim is to know primitive central idempotents of the rational group algebra. So how do you get that? For that, this is a classical method which I am talking of. There's an automorphism group of C. This acts on the set of all irreducible characters of G by the natural composition map. This is an action which you can check. So this acts on this. So this irreducible characters will get divided into orbits. Now on one side I have distinct orbits of irreducible complex characters of G, and then on other side I have primitive central idempotents of the rational group algebra QG, and there's a 1-1 correspondence between these two, that if I have an orbit of chi, then what you do, you just add, you see, remember this E psi was my notation for this. It's a primitive central idempotent of CG corresponding to the simple component from where chi is coming. So you just add those simple components of CG corresponding to those characters which are in this orbit. You just add them up. And then this fellow is this only, because I am taking psi in the orbit of chi, and one can check that the orbit what you get is by applying the Galois action of q chi. Take the Galois group of q chi over q and apply the sigma to chi, and this is precisely the orbit of chi. The orbit of chi you will get as sigma composed with chi, where sigma is in the Galois group of q chi over q. And so this is precisely this, and this is a primitive central idempotent of, now this is a guy in QG, rational group algebra, and it's a primitive central idempotent of QG, and this is a standard notation that it is denoted by EQ chi. Well, nice, it's a primitive central idempotent of QG. So the question is, we can apply this to get these PCIs. But in practice, it's tough to know. First of all, given a chi, it is tough to know what is this character field. To Q, I have to adjoin all the character values. First of all, it is difficult to know this character field. And then it is difficult to know this Galois group. So these computations are not so easy for practical purposes. That this theoretical method is good, but for practical purposes, this is not applicable very efficiently for large groups, that one is not able to do this computation with this method. So these are the drawbacks of this method. One should know this Galois group, one should know this corrector field, and so on. And moreover, another drawback is that supposingly somehow with some great effort you are able to do this computation, but then after knowing this PCI, do you know what is this algebra? This is a simple component. What is this as a matrix algebra over division algebras? What are those division algebras? What are the size of those matrices? So this method also does not reveal any information on that side also. So people tried to dig more into it, and they were interested in knowing this information precisely from the information of the group G, that can you play with the subgroup structure of the group, just stay within the group, and then you give all this information of PCIs and the Wedderburn decomposition. So why people thought of giving this information in terms of the subgroup structure of the group? So that is the first question, that can you write some idempotent from subgroups of the group? And the answer is yes, at least some idempotents you can write down. For example, if H is a subgroup of a finite group, then you compute this average sum. It's an element of QG and it's an idempotent, you can check. And this idempotent is central if and only if H is normal in G. So normal subgroups of G give you some central idempotents of rational group algebra. But these are some central idempotents, but my aim is, I'm interested in the primitive central idempotents. And then there was this result of Segal, which gave the initial input, proved in 1978. He proved that if G is an abelian group, then primitive central idempotents of QG are Z linear combinations of these H hats. This is my H hat, where H runs through subgroups of G. See, in an abelian group, all subgroups are normal, so I'm not saying normal subgroups. So it's a Z linear combination of H hat. Very nice. So you can write primitive central idempotents from these very nice looking idempotents. And but this description of Z linear combination was missing in the Segal's result, but it was later given by Jespers, Leal and Millies in 2003, that what are precisely these integral combinations. So nice result for abelian group so far, that at least you know that PCIs are Z linear combinations, and then it was more improved further. Am I okay till now? Hello?
Yes, you're fine.
Okay. So, yeah. So now we are moving from abelian groups to nilpotent groups, and then I will move further from nilpotent groups. So Jespers, Leal and Packwas in 2003 gave a fully internal description of the primitive central idempotents of QG when G is a nilpotent group from lattice of subgroups of G without making use of the characters. And then as a consequence, they improved the result of Segal, that even for nilpotent group, you can prove that every primitive central idempotent of the rational group algebra is a Z linear combination of H hat. And this result gave a forceful blow from abelian to nilpotent groups. And then this was a very, very important result to move further. And then this Oliveira, Del Rio and Simon from Murcia, they realized that what is at the back of nilpotent groups, which is playing a key role here in this picture, and they realized that it is the property of nilpotent groups being a monomial, that each irreducible complex character is induced from a linear character of a subgroup. So they push the theory from nilpotent groups to monomial groups, and in a very, very nice way. And so I will just introduce this notation because these are two important notations which I am using throughout. That if suppose G is a group and K is a normal subgroup of H is a subgroup of G, then epsilon HK is this group ring element. It's an element of the rational group algebra. M H over K is the minimal subgroups of H mod K. So it is something which is well written from H and K, and it's an element of QH. And then you just take all sum of distinct G conjugates of this element, and that is what this notation is, EGHK. So what you can see is that given H and K with this property, there is epsilon HK is some well-defined element of QH, and then if you take the sum of G conjugate, this is some well-defined element of QG, given from just given H and K. Okay, so what these Oliveira, Del Rio, Simon proved that for abelian groups, they try to see the expression of EQ chi. See, I talked about this expression of EQ chi. Yeah, this expression. So they started understanding this expression when chi is a monomial character. That what is this expression in terms of the group? And so they first saw it for linear characters and then improved it to monomial characters. So this is what they did, that suppose n is a normal subgroup of G with G mod n cyclic, then they proved that epsilon Gn is a PCI. So basically, if n is a normal subgroup with G mod n cyclic, then you have a linear character on G with kernel n, and they saw that EQ chi turns out to be precisely epsilon Gn. All right. And what is a simple component corresponding to this? And they proved that this simple component QG epsilon Gn is just isomorphic to Q zeta d. Zeta d is d is the order of G mod n. Having understood this, they tried to push to monomial characters. So what's a monomial character? A character induced from a linear character of a subgroup. When I'm saying characters, I mean complex characters. So if a character is induced from a linear character of a subgroup, then I call it a monomial character. And then monomial groups are the groups where all irreducible characters are monomial. And some example, monomial groups is a very, very large class of groups. Every monomial group is solvable, and every solvable group is embedded inside a monomial group. It's a theorem of Dade. Solvable groups can be embedded inside monomial groups. And these are some examples: nilpotent groups, metabelian groups, super solvable groups, abelian by super solvable, many more classes of groups which are monomial. And so what they proved in 2004 is that you take a monomial character and then it is induced from lambda. Lambda is a linear character of a subgroup H of G. Take K to be the kernel. I'm just going to give you one notation of a Schoda pair and then different classes of Schoda pairs, and because I need this terminology. So this lambda is on H and K is the kernel of lambda. Then this pair H comma K has these two properties. K is a normal subgroup of H, H mod K is cyclic. Of course, lambda is a linear character on H with kernel K, H mod K is cyclic. And then this property holds. This property holds because lambda induced to G is irreducible. So lambda and the conjugate of lambda will not have any common constituent on H intersection with HG, and this is what this result is. So if lambda induced to G is irreducible, then this pair will have these two properties, and this is what these guys called such pairs as Schoda pairs of G. So any pair H comma K of subgroups of G which have these two properties is called a Schoda pair of G. So Schoda pairs of G tells you what? They just give you monomial irreducible characters. So once you have a Schoda pair, take a linear character on H with kernel K, induce it to G, I am going to get an irreducible character of G, and it's a monomial irreducible character of G. And so this is what Schoda pair is. This is what I have told you, that a pair H comma K of subgroups of G is called a Schoda pair if these two conditions are satisfied. So knowing a Schoda pair or knowing monomial irreducible complex characters is the same thing. For example, look at S3. Let me just give you some example of a Schoda pair. Look at S3. S3, there are two linear representations. Again, I will say when I talk of representations or characters means complex ones. Two linear representations. One is the identity, and identity representation will correspond to the Schoda pair G comma G. It's on G and its kernel is G. And the other representation is linear on S3 with kernel A. And so it will give you the Schoda pair S3 comma A. And there is one non-linear representation which is induced from non-identity linear representation on this subgroup A. And so it will correspond to the Schoda pair A comma 1. The kernel of that non-identity linear representation will be 1. So this will give you this Schoda pair. So knowing monomial means knowing Schoda pairs. And so what these people prove that if you have a Schoda pair, then alpha EGHK is a PCI of QG. Remember, EGHK is a precise group ring element from H and K, which I have already defined. So a rational multiple of EGHK is a PCI. So what they took the monomial representation corresponding to this and try to understand what is EQ lambda induced to G. This is what they proved. But what is the simple component? What is the structure of the simple component corresponding to this idempotent? They were not able to say in general, but by imposing certain constraints on the Schoda pair, they gave the structure of the simple component. So what is that constraint which they had to impose? But this is an important constraint which plays a great role in the next theory which I am going to say. That a Schoda pair H comma K is called a strong Schoda pair if H is normal in the normalizer of K in G, and these two are orthogonal. So these are some, you just know that these are some additional constraints which he is imposing on the Schoda pair, and these constraints are so imposed that they were able to give the structure of the simple component. So this is a theorem which they proved that if you have a strong Schoda pair H comma K, then QG, in fact, if you have a strong Schoda pair, then that I told you this is a PCI, but then they proved that if you have a strong Schoda pair, this alpha is 1. So only EGHK is a PCI. And so one is interested in this simple component, and this is a matrix algebra over this cyclotomic algebra. They gave, it's a beautiful result. This cyclotomic algebra is simple, and this was a nice result which pushed the theory still further, which I'm coming now. So by imposing certain constraints on Schoda pairs, they were able to write down the simple components, and the groups where all primitive central idempotents come from strong Schoda pairs, they are called strongly monomial groups. And then some examples of strongly monomial groups. As an example, they proved that abelian by super solvable groups. This is the class of groups where every primitive central idempotent comes from a strong Schoda pair. Now, just coming to this strong Schoda pair definition. So suppose you have a Schoda pair with just H normal in G. Just take this constraint H normal in G. Then these two are easily satisfied. One can show. And so it's a strong Schoda pair. So if you just impose this condition on a Schoda pair that H is normal in G, it becomes a strong Schoda pair. And these Schoda pairs we call as extremely strong Schoda pairs. So another subclass of strong Schoda pairs. So the question is how to write down Schoda pairs, strong Schoda pairs, extremely strong Schoda pairs of a group. And so on. So this is the question we took up, and with Maheshwari in 2014, we proved, we gave an algorithm to write down irredundant set of extremely strong shadow pairs. And this also gave us classification of normally monomial groups. Normally monomial groups meaning that each irreducible complex character is induced from a linear character of a normal subgroup. And this algorithm allowed us to improve certain existing functions of the gap package Vidhvanaten. You must be knowing this gap calculations. Most of you must be doing the algebras. And there is a package called Vidhvanaten in gap, which Vidhvanaten stands for Wedderburn decomposition of group algebras. It's a gap package to compute simple components of the Wedderburn decomposition of semi-simple group algebras. And it contains functions that produce primitive central idempotents. And of course, simple components. So I will just talk of these two functions which were earlier there. Primitive central idempotent by strong SP and then strong shadow pairs. With this introduction of the newer algorithm, the theory got improved, and then we provided these new functions, extremely strong shadow pairs. We improved the function of strong shadow pairs, and then primitive central idempotents by strong shadow pairs and extremely strong shadow pairs. And then we also provided a function in gap to check whether a group is normally monomial or not based on our work. This appeared in Journal of Symbolic Computation. And based on this work, we could improve a lot in the existing functions of Vidhvanaten, and this improvement was implemented in the Vidhvanaten 4.9. So I will just show you how much change it brought to the existing functions of Vidhvanaten at that time. So you just, I'm just comparing the old version and the newer version in terms of the time computations. So we just take a sample of groups of order 2000. For every order, we took at least 100 groups of a particular order, and then we did the time comparison. This is the old time taken by the old Vidhvanaten, and this is the time taken by the newer Vidhvanaten. And we are almost 1/3. Now the time taken by the newer Vidhvanaten is almost 1/3. If you look at this function, PCI is by STSP. So this is taking almost 1/3 of the time. And then we also took a sample of solvable and non-solvable groups separately. For solvable groups, it was a drastic improvement, because actually we are now giving a proper systematic algorithm to write down those shadow pairs. Extremely strong shadow pairs first, and then strong shadow pairs, and so on. So this is the time comparison. This is what we are getting now. So less than 1/6 of the time. So that was the kind of improvement it did to the Vidhvanaten functions. But for non-solvable groups, because we are only working with monomial groups which are solvable, for non-solvable groups it is almost the same. There is no improvement because we have not done anything for non-solvable groups. And then this was gap function for normally monomial groups, and we just were wondering how dense is the class of normally monomial groups in finite groups, and we just checked that for the groups of up to 500, 97.88% groups are normally monomial. So it's a pretty impressive class of groups where each complex irreducible character comes from linear character of a normal subgroup. And so, but of course we have not checked beyond the 500 at that time, but that was the limitation. So moving further from these strong shadow pairs business, remember Oliver, Del Rio and Simon, as I told you. How much time I have?
You can take another at least 10 more minutes.
10 more minutes, yeah. So moving further, as I told you that Oliver, Del Rio and Simon gave the simple component corresponding to a strong shadow pair. And so we wanted to improve that. And so we tried to see what relaxation we can do. So we defined a class of Schroeder pairs called generalized strong Schroeder pairs. This is a recent work with Goodlean. So from H to G, see, remember what was EGHK? Just take sum of G conjugates of epsilon HK. So we did not do that. Take intermediate subgroups between H and G, and then don't take sum of all the G conjugates of epsilon HK in one go, just take in parts. Take epsilon naught HK as epsilon HK, and then H1 conjugates of epsilon naught, and then H2 conjugates of the previous one, and so on. So keep summing them up, and the last sum you denote by this EGHK, but this is a frank EGHK. This is different from this EGHK. One should not be confused with these two E's. And so this is the definition of a generalized strong Schroeder pair we gave, that a Schroeder pair is called a generalized strong Schroeder pair if there is a chain of subgroups of G with these two properties. See, what they did for strong Schroeder pairs in one go, we are doing in multiple steps. We are repeating the same process again and again. But this simple idea of repeating the process again and again gave beautiful results in terms of generalization. It really took the class much further, that you just take that these two conditions are satisfied at every step. From here to here, these two conditions, from here to here, these two conditions. They look very strange conditions, but I will show you that you cannot find any group. It's a challenging problem to find any group where these two conditions are not satisfied. Monomial groups where these conditions are not satisfied. I will come to that. So you impose that condition, and after imposing that condition, what we could do, we could provide the structure of the simple component. These are, we call them generalized strong Schroeder pairs. And then we also proved that this construction of EGHK now does not depend upon this chain, because initially this construction of EGHK depends on the chain, because every time you're summing here and then you're summing here and so on. So, but we proved that if it's a strong inductive chain, we call this as a strong inductive chain if these two conditions are satisfied. So this does not depend upon this. If it's a strong inductive chain, then this EGHK does not depend upon what series are you taking. You may be having different people may be having different strong inductive chains. So we gave the structure of the simple component for a generalized strong Schroeder pair. It's a repeated matrix algebra it's a cyclotomic algebra, and then matrices over this, again the cross product, again the matrices, again the cross product, repeatedly, because we are repeatedly doing the same thing. But the issue is how good is this generalization, how far we have moved with this generalization. Every strong Schroeder pair is a generalized strong Schroeder pair, because that is a one-step process and this is a multiple-step process. So all strongly monomial groups are generalized strongly monomial. We call a group to be generalized strongly monomial if every primitive central idempotent of QG is realized by a generalized strong Schroeder pair of G. And then we proved that all subnormally monomial groups are also generalized strongly monomial. Subnormally monomial means that an irreducible character of G is coming from a subgroup which is subnormal in G. From H to G, there is a subnormal series. And so all subnormally monomial groups are generalized strongly monomial. We also proved that all finite groups where subquotients of G have the property that either it is abelian or it contains a non-central abelian normal subgroup. It's a pretty large class of groups. And this class of groups we have proved is generalized strongly monomial. And these are some more classes of groups which we proved: monomial Frobenius groups, Kamina groups, and some more classes. I will just sum it up in this chart. Can you see this chart? Yeah. So this is where this class is. This is the class of generalized strongly monomial groups. It is inside monomial groups. Inside this, you have strongly monomial groups. Inside this, you have abelian by supersoluble. So these are all the classes of groups which we have proved are here. Groups in which each subquotient is either abelian or has a non-central abelian normal subgroup, subnormally monomial groups, solvable groups with elements of prime power order, Kamina groups, monomial Frobenius groups, and many more classes. So this was we proved. We also recently, but this result is published in Journal of Algebra last year. And recently we have some more results. This is under preparation, that monomial groups of order PAQB are generalized strongly monomial. Subgroup closed monomial groups are generalized strongly monomial. Super monomial groups are generalized strongly monomial. So these are some very, very nice indications of the fact that the class of generalized strongly monomial groups is huge. In fact, it also relates to Isaac's conjecture. Isaac's proved, conjectured that monomial group of odd order is super monomial. And what we have proved is that super monomial groups are generalized strongly monomial. So it also leads to a weaker version of Isaac's conjecture, which says that maybe one can expect, before Isaac's conjecture, one can expect that whether every monomial group of odd order is generalized strongly monomial. So if this is true, then we have almost closed the theory of giving the decomposition for monomial groups of odd order, say. And this I will not take up. The theory over finite fields I will not take up because the time will not permit me. But I will. We have done the similar computation for over finite fields for generalized strongly monomial groups, and they go really well. You can describe the structure of finite group algebra of a generalized strongly monomial group over a finite field. In the semi-simple case, precise decomposition, precise isomorphism, and all that we have given. So this research is still going on, and the problem is mainly group theoretic now, and we are interested in seeing at the closeness of generalized strongly monomial groups to monomial groups. And in the study of monomial groups, group theorists are interested to know whether normal subgroups, whole subgroups of monomial groups are monomial or not. And there are conjectures by Isaacs and Dade in this direction, and many positive instances by several leading group theorists to this fact, whether normal subgroups of monomial groups are monomial or not. For several classes, they have checked this result. And what surprisingly, we have found that all the classes of groups which have been taken up by these group theorists turn out to be generalized strongly monomial, which is really nice. That it's almost close to monomial groups, and at the moment it's like a challenge for us to see a monomial group which is not generalized strongly monomial. And we look forward to any answer to this question. This will be an excellent addition to this research. Thank you.
Okay, thank you very much. Yes, thank you, Gurmeet, for a very nice talk and very, very well organized. It's time for questions, and I see that Professor Ajit Iqbal Singh already has a question. I'll repeat it, and subsequently I would also encourage anybody else who has a question to just unmute and ask. So maybe I will read out. So her question is, can group algebra QG of non-isomorphic groups be isomorphic?
Yes. So this is isomorphism problem, that if the rational group algebras are isomorphic, then whether those group algebra, for example, in CG one can have, in CG, take any abelian group, say of order n, then CG will decompose as the n copies of C, but those groups you can take as non-isomorphic or morphic.
But her question was over rationals.
Yes,
rationals.
Go ahead.
Yeah, over rationals, yes, this is a problem, that if the rational group algebras are isomorphic, then this is an isomorphism problem, whether the groups are isomorphic or not. And a lot of positive instances of this, that if the rational group algebras are isomorphic, then the groups are isomorphic.
For CG, if you give them a norm, then they are not. So functional analysis recognizes the difference between groups.
Yeah.
What I want to say is, if you give the norm to CG, where you take complex numbers, then the group algebras of non-isomorphic groups are non-isomorphic. So functional analysis recognizes the difference between groups.
Okay. So you give the norm to that. Okay.
Yes, give the norm to that.
Okay, then they recognize that these are different
that
lines.
is some of the absolute values of the coefficients.
Okay, okay, okay.
Cheyenne has a comment. You want to say it yourself, Cheyenne? Unmuting.
I just said that for finite groups, I think there is no difference between this functional analytic group algebras and group algebras. So yeah, what he said, Professor Gurmeet, I think it holds true for like for finite groups. I mean,
It is for finite only.
sorry.
No, there is a difference. You see, if you take the norm, L1 norm, then the two group algebras will not be isomorphic when you equip with norm.
Yeah, but
equal, not isomorphic, isometrically isomorphic.
Are you saying that the group C star algebras are different than group algebras for finite groups?
Yes, but isometrically isomorphic.
Okay. I'm a bit confused now.
I'll give you the page number and all that. Palmer's book has computed it fully.
Okay.
Okay.
Maybe I would also like to. I would also like to.
Yes, I wanted to point this out. So in functional analysis, this difference is recognized via isometric isomorphisms.
Okay.
Are there any other questions or comments?
And have you seen Geeta Venkatraman's book with Blackburn and Peter Neumann, which gives enumeration of finite groups? Do you use that in your GAP program or anything?
No, I've not seen that.
But book, okay, this is Geeta Venkatraman, who's seen in most conferences.
Okay. I'll check up. I've not seen that.
Okay.
Okay.
Peter Neumann is the son of a famous Neumann couple.
Yeah, BH and Hannah Neumann.
Yes.
I had a simple question. Is it true that a super solvable group is normally monomial?
Super solvable? No.
It need not be, huh?
No, need not be. There are counterexamples.
So, and then for normally monomial, can you say that the converse of Lagrange is true for finite normally monomial finite groups?
For finite normally monomial groups, converse of Lagrange's theorem.
Important groups, but not for solvable or super solvable. That's why I asked.
Okay. I've not seen that. Maybe that's a nice question. I will just check up. Yeah, I'll just check up.
Okay. So if there are no further questions, let's once again thank Gurmeet again for a very nice talk.